Hello, my name is Xiong. This presentation is part of my NRF CRP application. Today, I will begin by introducing my background and scientific achievements. Following that, I will present my proposed research, covering the background, motivation, a competitive scan, the main objectives, the proposed approach, and the expected deliverables. First, let me begin with my background. I joined NTU as a Nanyang Associate Professor this January. Before that, I was a Principal Researcher at Microsoft Research Asia and an Associate Professor at the University of Massachusetts Amherst. I received my PhD degree from the University College London. My research interests lie in wireless sensing, mobile computing, mobile health, and smart IoT systems. My research has received numerous prestigious awards, including the 2025 ACM SIGMobile Rockstar Award, which is presented to one researcher globally each year. I have also received the ACM SIGMobile Test of Time Award 2024, the Mobicon 2024 Best Paper Award, as well as Best Paper Runner-Up Awards in 2020, 21, and 22. In addition, my work has earned Best Paper Awards from ACM Census 2022, Ubicon 2021, CONEX 2014, and IEEE SECON 2022. My current citation count is 9,800, and the Edge index is 51. NTU is currently ranked 4th globally in mobile computing according to CS rankings, where I am the key contributor. Early in my career, I received the British Computer Society Distinguished Dissertation Award runner-up and also the Google Doctor Fellowship during my PhD studies. My prior research at the University of Massachusetts Amherst was supported by highly competitive grants, including the NSF Career Award and the NIH R01 Award. The title of my proposal is a Quantum Wireless Sensing, Theories, Breakthroughs, and Applications. Our goal is to integrate quantum technologies with wireless sensing to revolutionize the next-generation wireless sensing systems. Wireless sensing is a new research area that emerged in 2013. It uses the wireless signal itself as a medium for sensing purposes. Pervasive signals like Wi-Fi can now be harnessed for sensing. Its sensor-free and contact-free nature has attracted significant attention from both academia and industry. Companies such as Google, Amazon, and Xiaomi have released products based on wireless sensing. On the other hand, quantum receivers offer several unique advantages over conventional RF receivers. They operate with extremely low noise levels and can detect signals across an exceptionally wide frequency range, thousands of times broader than traditional RF receivers. Quantum receivers also offer opportunities to overcome fundamental limitations in classical wireless systems. For example, conventional RF antennas cannot be placed too close to each other, leading to large-size antenna arrays. Quantum receivers, however, have the potential to break this antenna spacing limitation, enabling more compact and deployable antenna array. Recently, the 2025 Nobel Prize in Physics was awarded for advances in quantum tunneling, and Google just announced major breakthroughs in quantum computing. These milestones underscore the timeliness and transformative potential of quantum wireless sensing. Now, let me give you a brief introduction to the basic principle of wireless sensing. On the left-hand side, we have a Wi-Fi transmitter and a Wi-Fi receiver. The signals propagate along direct paths and also along reflection paths. The signals get reflected from the static wall and also get reflected from the human body. The direct paths and the reflection paths from the wall are in green color. They are called static paths. The signal reflected from the human body varies with the human's chest displacement. This signal is in red color and called dynamic signal. At the receiver, the static and dynamic signals mix together. On the IQ plane on the right-hand side, the mixed signal is shown in blue, and you can see it varies with the human's chest motion. So by analyzing these variations, we can extract the target's chest displacement information. For quantum wireless sensing, we use a quantum receiver to replace a conventional RF receiver. Now, let me briefly introduce readable atoms, which form the foundation of the quantum receiver. An atom consists of a nucleus surrounded by electrons. When the outermost electron is excited to a very high energy level, typically above 20, the atom becomes a readable atom. A readable atom can absorb RF signals by causing its electrons to transition between energy levels. By precisely controlling these energy levels, we can select the specific signal frequency we want to receive. For example, to capture a Wi-Fi signal, we excite the outermost electron to a particular energy level, which can be calculated in advance. By adjusting the electron to different energy levels, we can tune the readable atom to receive different RF signals, such as millimeter wave signals. Now, let me go through the competitive scan. Quantum wireless sensing is a very new field, first proposed by our group in 2023. Our initial results, published at Mobicon, attracted significant attention worldwide. The entry barrier for this new field is still high because the hardware is quite expensive. Two groups from the University of Hong Kong and Hanyang University are following our work, but their research is mainly simulation-based with no experimental testbed. Therefore, at this stage, we believe we have no direct competitors, giving us a clear lead in experimental quantum wireless sensing. Now, let me present our main research objectives. Objective 1. We will develop the theoretical foundations of quantum wireless sensing. These theories will help researchers understand the underlying principle and guide the design of future quantum wireless sensing systems. Objective 2. Most sensing tasks can be decomposed into distance, angle, and velocity estimation. We will push the performance boundaries of these key sensing dimensions to an unprecedented level. Objective 3. We will prototype 3 emerging quantum wireless sensing applications which were previously unattainable to demonstrate the transformative impact and practical potential of quantum wireless sensing in real-world scenarios. The targeted applications include real-time sub-millimeter precision 3D tracking for remote surgery, non-invasive blood test utilizing low-frequency everyday RF signals to perform rapid contact-free blood analysis, and Wi-Fi-based through-wall vital sign monitoring enabling continuous contact-free measurement of psychological parameters for healthcare. Now, let me briefly explain how we plan to achieve these ambitious objectives. For theory development, we will design a new metric analogous to signal-to-noise ratio in communication to characterize a signal sensing capability, taking into account the unique property of a quantum receiver. We will also develop signal processing techniques to extract phase information and further enhance signal clarity through more fine-grained hardware tuning. Our collaborator, Prof. Zhao, is a world-leading expert in theoretical quantum physics and quantum optics hardware. We will work closely with him to enhance signal feature clarity. To address the challenge of signal superposition, we will apply deep learning models to capture the complex relationship between signal variations and target information. While the inherently low noise of a quantum receiver is a key advantage, we will also explore additional schemes, including signal processing, hardware design, and machine learning techniques, to push the performance boundaries of a distance, angle, and velocity estimation. For example, in angle estimation, we will leverage the quantum receiver's extremely wide frequency range to perform frequency hopping, effectively creating virtual antennas and achieving even more precise angle measurements. Other directions include investigating whether quantum receivers can overcome antenna spacing limitations, which currently fundamentally constrain the size of antenna arrays. For application development, we will implement the sensing applications and collaborate with the Lilly Center at NTU, a university-level research center focused on designing computing technologies for the elderly, equipped with extensive experimental facilities. This collaboration will enable us to deploy and test applications in long-term, large-scale experiments. Our team PI, Prof. Miao Chunyan, has extensive experience in managing large-scale, multidisciplinary collaborations, ensuring the success coordination of this effort. The final deliverables will span the theories developed to lay the foundation for quantum wireless sensing, the signal processing schemes, hardware designs, and machine learning techniques developed to enhance sensing performance, We will grant access to our testbed to other research groups in Singapore to validate their theories and methods, as not every group has the resources to build a laboratory equipped with the quantum devices. We believe this will help boost the collaboration and strengthen Singapore's research ecosystem in quantum technologies. We will deploy the implemented prototypes in collaboration with the Lilly Center. Additionally, we will present our research outcomes to local hospitals and medical equipment companies to explore potential collaborations, aiming to translate our laboratory demonstrations into real-world applications. The research outcomes will also be disseminated to the broader community through publications in top-tier conferences and journals. To summarize, this proposal represents the first systematic exploration of integrating quantum technology with wireless sensing, a new direction with the potential to transform academia, industry, and education. It will help establish Singapore's leadership in this emerging subfield of quantum science. The PI's long-term educational goal is to train the next generation of researchers to adopt a multidisciplinary approach, empowering them to drive groundbreaking innovations in quantum wireless sensing and related fields.